Let me start thanking you, Angela, Monica, Miles, for this nice invitation. It's a pleasure to speak here about this. This is a paper joined with Alessio Figali, Xavier Rosoton, and Joaquim Serra. That appeared, that recently appeared already. So we finished this in the summer of 2019. You can also find it in archive, of course. So it's about the regularity of stable solutions to reaction diffusion equations or semilinear elliptic equations, and they turn out to be regular, smooth, up to dimension 9, as the title says. So let me explain you the story and the result. So, okay, everybody knows what is a semilinear elliptic equation. Here it is, the simplest one, diffusion, reaction, posed in a bounded domain of Rn, omega. We know that it is associated with an energy, kinetic energy minus potential energy, where capital F is a primitive of small f. Okay, so the first variation is our PD, and then we can make the second variation, right? And this is a quadratic form associated to an operator, which is the linearized operator of the equation at the solution U, right? And this is minus, the operator is minus Laplace minus f prime of U, right? So minus Laplace is a positive operator, say, and f prime, later on, we will take f prime to be positive. So if the minus is negative, so here these two guys are competing. Minus Laplace is positive, minus another positive thing. This could have negative eigenvalues or not when they don't exist. So when the second variation is non-negative, it's when we say that the solution is stable. So non-negative means exactly that the operator is non-negative definite among functions that vanish on the boundary, or if you want, infinity functions with compact support in omega. So here the test functions xi are functions that must vanish at the boundary, of course, all right? Because when we speak about minimizers of the energy or local minimizers of the energy, note that I didn't write any boundary condition. So when we speak about minimizers or local minimizers, it's always about competitors that have all the same boundary values as the solution itself. So the competitors, here you see them, have same boundary values as you. This means that xi, the test function here, must vanish on the boundary. Okay, so that's the game, right? That's the game. So for instance, a local minimizer of this solution is a solution that under small perturbations of this type has the smallest possible energy, small perturbations. Of this type means that xi vanishes on the boundary. And therefore, local minimizers are stable solutions. So stable solutions are a little bit, is a class a little larger than local minimizers if you want. But if you prefer to have in mind local minimizers, that's fine. Okay, that's the class of solutions. And what about the nonlinearities? Well, our interest, as you will see, comes from a problem in combustion theory, and the nonlinearities that we are having in mind are those which are non-negative and even superlinear at plus infinity. These are the nonlinearities which are bad. These are really reacting nonlinearities, right? Because they are non-negative and they are powerful, say superlinear at infinity. So these are the nonlinearities for which estimates and regularity is difficult to prove. An estimate for the solution are hard to prove, right? In particular, for these nonlinearities, no absolute minimizer exists, of course, because the energy The first term in the energy is quadratic, while the second term at infinity grows faster than quadratic because the nonlinearity grows faster than linear, and therefore the functional is unbounded below at any ray. Take any function xi with compact support, make any ray, and the functional becomes unbounded. So there are no absolute minimizers, but as we will see, there will be local minimizers, and therefore the paper says non-empty, and we will see this in a second. Well, in this slide, the main motivation comes from combustion theory and a model which is called Frank Kamenetsky model from the 30s that got known in the mathematical community in the 60s when Barenblatt wrote a chapter for a volume edited by Gelfand, and he spoke about the Frank Kamenetsky model that in a simple situation reduces to a simple, simple to write equation, which is our semilinear equation, with the parameter lambda in front of the nonlinearity. And then U is a temperature is the temperature of our gas, say, in a container omega, and it will be positive, and 0. We keep the boundary of the container at 0 temperature, right? And we think of F to be positive, even at the origin, non-decreasing, convex, and superlinear at infinity. And these are the assumptions that appear already there, and in all the literature right after it. The model nonlinearity that Barenblatt took is the exponential because of Arrhenius' law in chemical kinetics, right? And it satisfies all these properties. Another model would be the power nonlinearities with a 1 plus u, because here I like to have f of 0 positive. I like f of 0 to be positive because then for lambda positive, 0 is not a solution of the problem. 0 is a strict subsolution, but not a solution because f of 0 is positive. Therefore, there is no trivial solution to the equation when lambda is positive, but it's very simple to prove that there exists a parameter, lambda star, that we call the extremal parameter. And for every parameter lambda between 0 and lambda star, there exists a solution which is positive. Recall, 0 is not a solution, right? There exists one solution which is positive. It's classical, so bounded, and it is stable, right? And these solutions form a branch. Increasing in lambda, the solutions increase as lambda increases, and they converge to a weak solution that in principle, the only thing we know is that, or pretty much the only thing we know is that it's an L1 function, and it's a distributional stable solution for lambda equals lambda star. And we call it the extremal solution of the problem. At the same time, for lambda bigger than lambda star, there are no solutions, even in a very weak sense, no solutions at all, okay? In the model, what happens is that you have a reactive gas or product, which is initially, consider the heat equation, evolution with time. Initially at time 0, it's at 0 temperature, right? Uniform 0 temperature all over the container. But then there is reaction, you see, even if U is 0, f of 0 is positive. So there is a reaction and the temperature is going to increase no matter what, with time. It's going to increase with time. And there, the model is an ignition model. So what happens in reality is that if lambda is less than lambda star, the temperature will increase. There will be no ignition, or say real combustion or ignition. And instead, the reactive product goes under oxidation. They call it oxidation, and it doesn't burn, and it reaches, as time goes to plus infinity, a stationary temperature, which is exactly the solution of this problem, the stable solution. And you see that. And there was no explosion or ignition. Instead, for lambda bigger than lambda star, it's when ignition succeeds to happen. All right. Well, this is the model. All right. So what we are going to care is about the regularity of stable solutions. All these ones are bounded for lambda less than lambda star, but the lambda star solution, which is U star, it's called the extremal solution. This, in principle, could be bounded or unbounded. In principle, it's not simple to determine this. The first paper that there was on the subject was in 1972. Joseph Landgren studied the radial case by phase plane analysis for the power and for the exponential nonlinearity. Let me tell you what happened, what they saw, what they proved for the exponential nonlinearity. They saw, so here the domain is a ball and everything is radial. Up to dimension 9, the branch of stable solutions, which is here, you see my pointer, I guess, right? Yes, I think so.
Yes.
Good, thanks. In L infinity norm remains bounded, and therefore the extremal solution is also bounded. Then by the implicit function theorem, there are no solutions for lambda bigger than lambda star. The linearized operator has positive first eigenvalue here, positive fourth. Here it becomes 0. So this solution is still stable, but like degenerate stable. And then the branch must turn by the implicit function theorem, and these solutions here are unstable, are not stable, are unstable. And then the branch in the unit ball starts bending and turning, and has infinitely many turning points and a vertical asymptote here. For dimension 10 and higher, the picture is simpler. The L infinity norm of the stable solutions blows up as lambda goes to lambda star, and the extremal solution is not bounded. It's a weak distributional solution, but it's not bounded. This was done by them by ODE techniques, but at least something, part of this is easy to understand from PDE techniques, very simple PDE technique, which is this one. This was pointed out by Bresis and Vasquez later on. This argument. There is explicit singular solution. Here it is the logarithm of 1 over x squared, which solves the Gelfand, this we call Gelfand equation, okay? For this parameter lambda here in the unit ball, it's 0 on the bound. This function is 0 on the boundary. It's positive in the unit ball, and it solves the problem for this parameter in dimension 3 and higher. It's a singular solution because it's a logarithm. Now you should look at its stability. Is it stable or not? Well, that's very simple. You make the linearized operator, it's minus Laplace. The derivative of the exponential is the exponential itself, and the exponential of u is 1 over x squared. And this is a very nice operator. It's a Hardy type operator, and therefore we know that this operator is coercive or positive definite, if and only if this constant here, 2 times n minus 2, is less or equal than the Hardy constant. And therefore, if you make the algebra here, it means n minus 2 greater or equal than 8, n greater or equal than 10. So the explicit singular solution, which is the logarithm, is stable in dimensions, in the unit ball, in dimensions 10 and higher. So it could be that it is the limit of the stable solutions, and in fact it is. But this argument does not prove that, but almost. Instead, in dimensions up to 9, this solution is here, is on the top of this vertical asymptote, and in particular, this parameter here is 2 times n minus 2. for up to dimension 9, and it is very unstable, this solution. In fact, it has infinite negative eigenvalues corresponding all these infinite turning points. Okay, so this is in the unit ball, and it gives a first answer. In low dimensions, the stable solutions are uniformly bounded. In higher dimensions, they are not. All right. Okay, for the powers, the similar thing. There are explicit solutions. You make the same computations, and you get that they may be stable, but only in high dimensions, in dimension 11 and higher in this space, always in the unit ball. Right. All right. So the question is this: when is the extremal solution bounded, or more generally, when are energy stable solutions bounded? Once they are bounded, they are infinity, of course, because once you know they are bounded, a solution is bounded, then f of u, the right-hand side, is bounded, and by elliptic regularity theory, linear elliptic regularity theory, u gets better and better, and if the nonlinearity allows, you get all the way to C infinity. One comment: for general solutions, which by general means not necessarily stable, for general solutions, L infinity estimates are very hard to prove. And in fact, in general, for the reaction diffusion equation, they hold only when the nonlinearity is subcritical or critical, which is this, all right? But now we restrict to this special class of local minimizers of the energy, or if you want, stable solutions, all right? And we try to see if we can say more. Another comment, there is this problem is the PV analog of a very famous problem in differential geometry, which is the regularity of minimizing minimal surfaces, or more generally, stable minimal surfaces, hypersurfaces in Rn. So, so it is known, and there is an explicit example also, the Simon's cone, that in dimensions 10 and higher, when ambient space is of dimension 8 and higher, there are minimal surfaces, so surfaces with zero mean curvature, which are singular, and they are absolute minimizers of the area. So they are minimizers, even absolute minimizers, and therefore in compact sets, and therefore they are stable. And they are singular, they are like cones, the explicit cones. So the Simon's cone is the simplest. Okay, so this is the same as the logarithm, which is stable in high dimensions, 10. Here it's 8, it's okay. On the other hand, it is known, this is my last sentence, let me start by the last sentence. It is known that up to dimension 7, so the complement of these dimensions, in the rest of dimensions, minimizing minimal surfaces are always smooth. They cannot have singularities like conical points. So you have regularity for absolute minimizers of the area. Instead, if now you care about the more general class of local minimizers or stable minimal surfaces, the problem is very hard. And the regularity is only known up to dimension 3. So for two-dimensional surfaces in R3, all right? And this is a nice result proved independently by Fisher, Cabré, and Sean, and by the Carmo and Penn. So this is the 80s, the beginning, 1980. And the problem is still open. So the regularity of stable minimal surfaces in Rn is still open for n equals 4, 5, 6, 7. And this is a very famous problem, but very, very, very difficult, okay? So my work with Figali, Rosotton, and Serra takes the analog question, but for the reaction diffusion equation, thinking of nonlinearities of this type, exponential of u of 1 plus u to the p, that come from a model in combustion theory, right? So you don't have absolute minimizers, but the stable solutions appear in nature. For instance, as I told you, in this combustion problem, all right? In minimal surfaces, stable minimal surfaces, we also see them in nature. Stable and not absolute, which are stable minimal surfaces, which are not absolute minimizers, we see them in nature. In fact, some catenoids, if you take two parallel wires, coaxial, and you put soap film, and you when the two wires, circular wires, are very close, the catenoid is an absolute minimizer because it has more area than the two disks. It has less area than the two disks when they are very close. You start separating, and at some point, the catenoid will have more area, larger area than the two disks. And at this time, the catenoid is stable still, but it's not an absolute minimizer. But you can see it in a lab, or here in my room, I could see it. And it is later, at a larger distance, when the wires get larger, that this stable catenoid, which is not a local minimizer, loses its stability, and then it becomes the soap. If this is done carefully, it breaks and it becomes, you don't lose the soap, and it becomes the two. So this is an experiment some people did, and they becomes the two disks. Okay, so in nature we see local minimizers which are not absolute minimizers, even in minimal surfaces. Okay, so let's go back to our problem. And besides the radial case studied by Joseph Landgren, the first really important paper, a very beautiful paper, in fact, is by Crandall and Rabinovich in 1975. And now it's in every domain, say, so non-radial case. And what they proved is that the extremal solution is going to be bounded up to dimension 9 if the nonlinearity is the exponential or very close to the exponential in terms of some relations needed for f prime and f second. The function f, its derivative and its second derivative should satisfy a relation that makes that the nonlinearity is almost the exponential, but you can perturb a little. Or the same relation, in fact, the same relation for f prime and f second forces the nonlinearity to be either an exponential, multiplied by a constant, of course, or a power. So it's like an ODE that if you solve, you only have these possibilities. If the ODE is satisfied everywhere. You assume this at infinity. When U is very large, one needs to impose this ODE or a sign for the ODE at infinity. Okay, so anyway, the paper arrives to the optimal dimension 9, because recall at dimension 10 there is a counterexample. In the radial case, the extremal solution is a stable solution which is unbounded. It arrives to this dimension, but for a very small class, say, of nonlinearities, very close to the exponential or powers. Okay, so the questions are clear now, and the problem. Okay, 75. So 20 years later, the problem was retaken with quite actively within the group of Brezis, because of some results of Brezis and collaborators about the parabolic problem, the parabolic Gelfand problem. Well, and some results were also elliptic, but they started with the parabolic. So, and at that time, in 1995, I arrived to Paris, and I was a postdoc there. So I got interested in the problem. So it was Brezis mainly who raised these questions Well, the one we are going to care here is mainly the second one. And Bresis in this paper wrote explicitly the open problem like this: is there something sacred about dimension 10? Or on the contrary, is it possible to construct a singular stable solution in smaller dimensions for some domain and some nonlinearity? So as you see, at that year, we still didn't know what was the answer. Bresis didn't know the answer. Nobody knew the answer. Another question that you find in another paper by Bresis and Vasquez is, for instance, is the extremal solution always in the energy space in H1 or not? So these are the questions. And the first result after Crandall-Rabinowitz was by a student, a PhD student of Bresis, Grégoire Nedev, in 2000. This was part of his PhD thesis. And he proved that the extremal solution, but then I'm talking here about, I'm writing this for the extremal solution, but the arguments work for every stable solution. So take your favorite, your reaction diffusion equation, even without a parameter, take a stable solution. The proofs pretty much, don't worry about this, they give an a priori estimate for any stable solution, not only for the extremal. And Nedev was able to get this up to dimension 3, okay? Yes, there is one important hypothesis that the nonlinearity must be in the class of Barenblatt. I won't go back. The class of Gelfand-Barenblatt is positive nonlinearity, non-decreasing, and convex, and superlinear at infinity. So if you want, think of always of this class. Okay, dimension 3, that was very nice. Dimension 2 and 3, okay? Even 2 is not trivial. Then I had a work with Antonio Capella, where we were able to get to the optimal dimension in the radial case for every nonlinearity. Here, really, we don't need any assumption on the nonlinearity. And this was 2005, and this gave hope. This gave hope for an affirmative answer, but we were still in the radial case. And in the non-radial case, the only definite result was another one by me in 2010, proving the result up to dimension 4. Also for any nonlinearity. Okay, so from then on, dimensions 5, 6, 7, 8, 9 remained open. There was some partial progress that I did with Rosoton or with Sanchon and Manuel Sanchon and Joel Sprague, but they are rather partial and they need assumptions on the domain or in the nonlinearity. So I will skip this. They were not really satisfactory. They were attempts. So this is the main theorem, the first theorem with Alessio, Xavier, and Joaquim. And it says a very simple statement, right? It says it's an a priori estimate in principle, and then you use it to prove regularity for the extremal solution. But take it as the tough thing, it's the a priori estimate. Take a classical solution of the reaction diffusion equation, which is stable in a ball. This is the interior regularity. So take it in a ball, no boundary conditions. So the solution is probably not radial. And the only assumption on the nonlinearity is that it's non-negative. This we need, non-negative. So the function u is going to be superharmonic, and we use it at some points. Then in every dimension, we can prove that the gradient of u is in L2, even a little more than L2. So it's an H1 a priori estimate, very nice one, because on the right-hand side, there is only the L1 norm of u and a universal constant. And this is in every dimension. Instead, for the L infinity estimate, we know that we need a limit for the dimension, and we arrive to the optimal dimension 9. So if n is less or equal than 9, then we have a holder interior estimate for the stable solution. So B1 half. So I go to the interior, and the exponent alpha and the constant here are universal in the sense they only depend on the dimension n. And again, the estimate is beautiful in the sense that, first, on the right-hand side, there is only the L1 norm, a very weak norm of the solution. Second, the nonlinearity does not appear here. So if you see, these estimates look like Gilbert-Schrödinger, right? Look like linear theory in Gilbert-Schrödinger. But the equation is nonlinear, so they are a little surprising. And that's why they are not so easy to prove. The problem is nonlinear, but the stability of the solution in some way, when you are in this class of stable solutions, it allows you to build something that looks like a linear theory and linear estimates, all right? So, okay, so the corollary of this is regularity up to the boundary in convex domains. Because it is known that when you have 4 non-negative nonlinearities and stable solutions, of course, always stable solutions, it is known when the domain is convex that singularities cannot approach the boundary. Near the boundary, because of convexity, everything will be fine. And this is proved using the moving planes method. And this was known for decades, okay? So in convex domains, near the boundary, the moving planes method gives you that the solution is monotone in the inner directions, and therefore if it's monotone, you control the L infinity norm by the L1 norm, and the L1 norm is controlled. And then in the interior of the domain, we use theorem 1. So this is an immediate corollary, convex domains. But then you care about non-convex domains. And what we are able to prove is regularity. You see here at the end, I don't know if you see this thing that appears in black for the slides, for moving slides, but it bothers me. I hope it doesn't bother you. It's when I move the mouse. Well, in this last line, it says, yes, we have also the holder estimate, but now up to the boundary, up to dimension 9. And what we need is the domain to be C3. That's okay. And we need the nonlinearity to satisfy some extra assumptions that F is non-negative, F prime is non-negative, and F second is non-negative. So we need non-negative, non-decreasing, and convex nonlinearities. And of course, since we are now here in this slide, let me tell you that it is an open problem to know, for instance, for theorem 2, if you can remove any of these assumptions. Or even for the theorem 1, it is not known if we can remove the non-negative of the reaction nonlinearity. It is only this F greater or equal than 0 can be removed in the radial case. And in the non-radial case, it can be removed in dimensions 2, 3, and 4 by the results from the previous slides. But in the rest of dimensions, this is still an open problem, say. But we are happy because a non-negative F is quite okay. Okay, and also we are able to prove, well, this was in the previous slide. Yes, here. The solution is in the energy space, even a little more integrability, but in the energy space, once it is in L1. And for this Gelfand problem, for this type of problems, to control uniformly the L1 norm is okay. Uniformly in the branch is okay. Or otherwise, you assume that your solution is L1 to start with, right? So, and this H1 estimate that solves an open problem of Recis Vasquez, this holds in every dimension, okay? but boundedness up to dimension 9. In dimension 10 and higher in the paper, we also find Murray type estimates, which are optimal or almost optimal, okay? But I will not enter on this. We get this with the same method of proof. So let me now describe the proofs, okay? So we will use two things, the equation and we will use the equation several times, and we will use the stability also several times. So this is the stability condition. And the point is to use it with appropriate test functions xi. So first thing you do is to write xi as the product of two functions. The second one, this is not well written. Here what I meant is that the second one is going to, eta, is going to vanish on the boundary because xi must vanish on the boundary. But the first one then, C, is free. And I will choose it later. And it will be a very important choice, C, the choice of C. And it does not need to vanish on the boundary because eta will vanish on the boundary. Once you put this function xi, a product of two functions, inside here, you manipulate a little, integrating by parts. It's very simple. And you obtain this relation, which is nicer than the first one in the sense that you see the linearized operator here acting on C. So the game now will be to choose appropriate C functions, which are appropriate in the sense that they satisfy something interesting for the linearized problem, right? All right. So this method in the reaction term, it was first used, say, well, I used it in this context with Capella, motivated by the Simon's lemma on minimal surfaces theory, on minimal cones. In the Simon's lemma on minimal cones, which is a very important result in minimal surfaces, what Simon's take is C equals the curvature of the cone or of the surface, the absolute, the length, the norm of the second fundamental form of all the curvatures, right? Okay, instead here, I wrote again the same thing here. Instead here, well, the papers by Crandall-Rabinovitz and by Nedev don't use this C function, and they work directly with xi, and they take xi to be a nonlinear function of U, right? And this allows them to get some results, but not too good, say. And the point is that they will choose H depending on what F is. But then you need some restrictions on F. This is the idea. Or just go up to dimension 3. So in the radial paper with Capella, what we took is this decomposition, xi equals C times eta, and we took xi to be UR or RUR. You can take RUR or UR, doesn't matter. UR is the radial derivative of the radial solution U, which is RUR is the same as X grad U, say, in the radial case. And then the eta function will be a power, a negative power of the distance to the origin, like in minimal surfaces. Minimal surfaces, you also take these negative powers of the distance to the origin. Like in hard inequality, you take, this is quite natural. But the important thing is how you choose C. And this is what we did in the radial case. Instead, in my paper in dimension 4, in the non-radial case, I took a very different test function, C, which came from a very important paper in Allen Kahn by Sternberg and Zumbrum, which is the modulus of the gradient. Of course, in the radial case, UR is also the modulus of the gradient, pretty much, because UR will have a sign, so it is the same. So in the radial case, UR is either X grad U, but it's also the modulus of the gradient, okay? But in the non-radial case, well, up to this year, 2010, so 10 years ago, there were, in the non-radial case, there were two test functions used. The one of Crandall-Rabinovich Nedev, and this one, modulus of gradient u, all right? Now, in the paper that I'm describing, with Alessio, Joaquim, and Xavier, what we do is that we use both of them. And the most important one that will bring us to dimension, that will give the algebra that gives you dimension 10 or 9, is this one, x grad u, right? So, okay, so look at the first line. I need to compute the linearized operator at my choice of function c. So I'm going to do it for these two functions. And for x grad u, it's very easy to compute the Laplace and then see the linearized operator. And the result is very simple. It's 2 times the Laplacian of u. And instead, for the modulus of the gradient, it's also a simple computation. And what you get is the squares of certain second derivatives. Not all of them, just some of them. You miss a column on the Hessian. You miss a column, okay? But this quantity here contains, inside here, you have at least all the curvature of the level sets of the solution. And this is like a geometric flavor and more similar to minimal surfaces because you play with curvatures. And this is what I used in my paper in dimension up to dimension 4. Level sets, their curvature, a Sobolev inequality with a geometric Sobolev inequality, beautiful one, which is called the Michael-Simon Sobolev inequality, for those of you who know. If not, I recommend that you look at this. And in this way, using this second test function, one can accomplish dimension 4. But now we are going to use the first. And remember what is the stability condition here. So here I will have C, which is x grad u, times 2 times the Laplacian of u, eta square. And this is in next slide, I think. Yes, here. X grad u, 2 Laplacian u, eta square. On the left-hand side, this is going to be bounded by c square. Let's go back to the previous. C square grad eta square. So x grad u square times grad eta square. Now this, you don't like second derivatives. Here you integrate by parts and you use the Pogozaev trick to make second derivatives disappear. This is just the Pogozaev trick. And what you get is the first lemma, which is crucial, which says for every dimension, for every nonlinearity, for every stable solution, for every test function vanishes on the boundary, you have this inequality. 3 terms less or equal than 0. And the terms are, let's look at the terms. The first one, well, involves the test function eta, that's still at free for us, but multiplies grad u square. The second term has x grad u, which is ur. Sometimes I will say x grad u, or I will say rur, or I'm using ur. It's the radial derivative. This for me is the radial derivative. And eta will be a function of the radius. So this will also be the radial derivative. Radial derivative is square. Instead here, grad u square. And here, radial derivative is square. Okay, so now what we want to do as in minimal surface theory is to take eta, to get information from this, and take eta a negative power of the distance to the origin. Here I'm fixing a point, the origin. It could be any point because the solution is not radial, but let's fix the origin. And I would like to get the power as negative as possible, to get as much information as possible from this relation. So as negative. But I cannot take it to negative because this is the key observation. The first term, 0 term here, in brackets, should be non-negative. Otherwise, I will not be able to get any information from this. Why? Because the first term is multiplying the gradient square. Imagine that this was negative, and then I imagine it positive on the right-hand side. So I would have the gradient u square on the right-hand side. And on the left-hand side, if something positive remains, it would be only the radial derivative, so square. So I would have the radial derivative square controlled by the gradient square on the right-hand side, this is not very useful because the radial is always smaller than the gradient u square. Maybe somebody knows how to get something from this, but we don't. So, zero, the brackets must be non-negative. And then if you make the algebra, this brings you that the most negative you can be, the power, the most negative is this one, 2 minus n over 2. Okay, so life is like this. And with this exponent, when I compute the derivative of eta falling here, this goes away. And it only remains a part when the gradient falls on theta. So what is going to be theta? Theta is going to be a trivial function. It's going to be 1, 1, 1, 1 everywhere, and then just 0 near the boundary. So it's going to be a cutoff, all right? So all this, when the gradient falls on theta, I will put all these terms on the right-hand side. Good, so when the gradient falls on the power, it gives you 0, this term. So now I have to look at what the term 1 and 2 give, and its sign in particular. So now for this guy, I look at 1 and 2. 1, I have to make theta square and differentiate it. Theta square differentiated, n minus 2 is going to come down with a 2 in front, 2 times n minus 2. And here I have to take the gradient of eta, gradient of this function, square. So this exponent square. So at the end, you make the computation carefully and you get something that multiplies this number here. And then you make the algebra and this number becomes n minus 2 times 10 minus n. So, so what you get, exactly what you get from all this stuff is this relation here at the end, that n minus 2 times 10 minus n times the integral of r to the power 2 minus n ur squared in a ball of radius, say rho, if you want, is controlled by a constant. And now the same quantity, but instead of ur squared with the full gradient, and instead of integrating in a ball, now integrating only on an annulus. This is very important, on an annulus. Because why the annulus here? It's just because the gradient fell into the cutoff function that was 1, and therefore it had no gradient in half the ball. It only has gradient outside the birro on the annulus. Okay, so this looks beautiful, but of course this brings you to the optimal dimension. You will get information if and only if n is less or equal than 9, right? N less or equal than 9, okay. So, okay, so this we had in fact for some years, more than 6 years, maybe 7 years, but the difficulty getting this, I mean, getting an L infinity bound from this was that here you have ur square and here you have the full gradient square, which in principle could be larger, right? So, but at the moment, suppose that you are in a convex domain and this is near, or you make another similar argument and this is near the boundary and you know that this is controlled, then if this is controlled because you are near the boundary, the left-hand side is also controlled. And the left-hand side, if you write it at center, not only at the origin, but at any point, being bounded is a lot of information, but not enough for an infinity. But it's very simple to see that this information here, with this potential here, it's easy to see that this proves that the solution is BMO, bounded mean oscillation, which is almost bounded, but it could be unbounded, okay? In particular, the solution is in LP for every P. BMO functions are LP for every P. So this we knew, well, at least I knew and I communicated to some experts for more than 6 or 7 years, but still we were stuck, okay? Okay, if we had, okay, this is what we have. If we had that in the annulus, our right-hand side, which is this, was controlled by the same quantity, but involving only the radial derivative instead of the full gradient, then we are done. Then we are done, because then the estimate that we have is for the radial derivative square with the weight. On the left-hand side, you have it integrated in a ball, here on the annulus, and then what is called the whole filling technique allows you to conclude. Most of you probably know, most of you must know this. If not, what you do is that, well, from this, what it gives you is that the integral in B rho is controlled by the same integral in B2 rho in a larger ball, but with a constant less than 1, because you bring this from the previous line, you get this. And therefore, these integrals decay algebraically as the radius gets half and half and half, okay? And then this is very easy to see that leads to the Holder continuity, of U. Because note that this quantity here is adimensional. It's like an L infinity norm of U is adimensional. This is also adimensional because here you have one derivative square, so this has dimension -2, which kills the 2, and then the Lebesgue measure counts for dimension n, but with the -n goes away. So if you rescale your solution, you still have a stable solution, but in a larger ball or a smaller ball. So our class of stable solutions is invariant under rescalings, and this quantity is invariant under scalings, okay? And this is why this is difficult to prove, because it's invariant under rescaling. So, but all this, we would be finished if we had this thing in red here. So the point was to control. And in an annulus, the weight plays no role because it goes outside, pretty much, because things, modulus of x is between rho and 2 rho. So next slide. So what we would like to prove is something like this in an annulus for a stable solution. Right? And may it be true this. And for many years, we didn't know how to prove this. And well, I made several visits to Zurich. I remember the first one telling the problem to, well, Xavier Rosoton and Joaquim Serra were my PhD students. They knew about the problem and we had thought together about it. Then I made several visits to Zurich, and I told the problem to Alessio, as I had told to other selected people, say, or people I could trust, right? I could trust. The first visit to Zurich, well, Alessio got very interested on the problem, but we didn't arrive to anything. And the second visit, we made progress getting the 4 of us together and putting all our strength together. So, and a key idea was heuristic idea was this one here. If false, then if this was false, in the extreme case, well, perhaps I can have the left-hand side to be 1 and the right-hand side to be 0. Is this possible for a stable solution? And the answer is no, it's not possible, because if U r is 0, then this function is 0 homogeneous. And I have, so if it's 0 homogeneous, it means that it's a function of the angles only, defined on the sphere. And it's superharmonic. Here is where I'm going to use that f is non-negative in the strongest way. Here, it's superharmonic, but there is no superharmonic function on the sphere unless only constants. But then if it's constant, this cannot be 1. Contradiction. But of course, this is an heuristic argument in the limiting case. But we succeed to prove this by compactness argument. using, and the compactness, we get it using a higher superharmonicity and a higher integrability estimate for the gradient, which is non-trivial to get and comes from using the other test function C, the modulus of the gradient, which leads to this higher integrability, thanks to Sobolev inequality and some arguments, of course. Let me say that but now we know how to prove this star without a compactness argument. Well, I know how to do it, and this will be soon a paper in archive, I hope in a month or something like this. So now we are able to complete I can give proofs of the full paper, the proofs of all the proofs in the paper without using compactness, which is nice because it's really quantitative. Everything is quantitative, and I could even tell you what are the exponents, Holder exponent alpha. I could tell you what it is because I don't rely on compactness. With the compactness argument, you lose track of what are the exponents, right? So that will be soon in archive, right? But anyway, we were very happy because we accomplished to close the circle, do the whole filling, and get Holder regularity up to dimension 9. And in the remaining 4 or 5 minutes, let me just tell you how it goes, the boundary regularity. It's very quick. Miles is
very
doing
quick.
something.
Very quick. So we have time for questions.
When I finish, you mean? Or I should finish at 25. You didn't tell me that. Let me
finish soon if you can.
Okay. Yeah, the boundary regularity, well, this is your domain. You cover it by small balls, very small here, very small, where the curvature is large. So they look almost like flat, but they are not flat, okay? And the first observation is that this test function that was crucial is good when the boundary is flat. Exactly, totally flat. Because if u is 0 on a flat boundary, x grad u is also 0 because it's a radial derivative along the flat boundary. And remember that the test function must vanish on the boundary, but the power does not vanish. Now it does not vanish, and neither the cutoff, because you want to arrive to the boundary. So, but we are saved because this is bounded, because this vanishes on the flat boundary. When the boundary is not flat but almost flat, we have to modify this, and technically is a kind of a pain. But we can do it, get to the similar thing. And now the question is, are there superharmonic functions which are zero homogeneous? So functions of the angle, but now not in the whole sphere, but in half sphere, and zero on the boundary of the half sphere in the equator. And unfortunately, and happily, the answer is that yes, there are. It's not like before that there are only constants. Now there are. For instance, this is an example. The sinus of theta is a superharmonic function. So superharmonicity is not enough, and this is my last transparency. But still, we should have hope, because even if there exist superharmonic functions in half the sphere, they should not solve a semilinear equation. Because if u is zero homogeneous, f of u is zero homogeneous, but minus Laplacian of u is minus 2 homogeneous. So this contradicts the semilinear equation. So the question is, because we are going to use a compactness argument, can one pass to the limit condition, can one pass to the limit in the semilinear equation? Because I will have a family of stable solutions, UK, family of nonlinearities, think that the nonlinearities can be very bad, like exponential of exponential of exponential. So this is a very delicate question, and it's one of the most difficult parts of the paper, say, and we are able to be able to pass to the limit and say that in the limit there is a stable solution for some nonlinearity. And this will contradict, this will allow to make this contradiction argument. But we need the nonlinearities to be non-negative, non-decreasing, and convex. Did I forget non-negative here? Or maybe we don't need non-negative in this lemma. In this lemma. So what it says is that the family of stable solutions, when the nonlinearities are non-decreasing and convex, are closed. And the limit, if you have a family of stable solutions that converge to somebody in L1, the limit is in the energy space and its stable solution for some equation, some F that is non-decreasing and convex, like compactness theory for harmonic functions, right? But for stable solutions of semilinear elliptic equations. So thanks a lot for the attention. And this is